Hello, General Biology, and welcome to the second in the screencast series for Chapter 2. We're still on Section 2.1. And when we left off, I kind of ran over a little bit. I was so excited about the atom that I wasn't watching the time. So it kind of, you might have had a little cut off at the end abruptly. So we were talking about the periodic table of elements. And if you do have your red book with you, it is in your red book in the reference pages, and you can open that up. If you have the textbook with you that I gave you, the older version of the textbook, you can open that up into the back section and you'll be able to see a periodic table of elements. We'll go over that periodic table of elements in class and we'll familiarize it with you. But one of the things that you need to know and we need to continue talking about is we're getting ready to talk about isotopes. We've already said that the number of protons and the number of electrons are going to equal, making that atom electrically neutral, but the number of protons and the number of neutrons do not have to be equal. And as long as we have this proton number staying consistent, then we're going to have this same element. The element doesn't change, just the weight or the mass of that element is going to change. So let's take a look at that so we can explain that a little bit further. What we're describing is an isotope, and isotopes are atoms of the same element that differ in the number of neutrons they contain. So there's your definition. So let's take a look. If we have a regular carbon atom and it has 6 protons and 6 electrons, we know that it's electrically neutral, and the number of neutrons is 6. So when we figure out the mass, in order to figure out the mass of an atom, we have to take the number of protons plus the number of neutrons. So 6 plus 6 is 12. We would call this type of carbon carbon 12. Because carbon-12 indicates the mass of it. Now notice this word non-radioactive. We're going to get back to that in a minute. So we're not going to focus on that just yet. But sometimes with carbon, what can happen is this number of protons can differ in the number of neutrons. So that when we add this together, we're going to get 13 as the atomic mass. So we're going to wind up calling this type of carbon carbon 13. It's still carbon because it has 6 protons, but the weight of it is different because it has 7 neutrons. Now remember I said to you that the electrons are in constant motion. They're constantly spinning around that atom. Well, guess what? That nucleus is constantly spinning as well. So think about a ceiling fan. When a ceiling fan spins and it's balanced, it's going to spin really kind of quietly, smoothly, and nicely. But what if we were to throw it off balance? What if we were to add another blade but we didn't balance those blades out? It's going to start to wobble, right? And when it starts to wobble, sometimes you're going to get a noise, and noise is a form of energy. So here's what happens when we add just one more proton to the mix. So now here we have six protons, so that's still carbon. We're going to add 2 neutrons. So from 7 we're going to go to 8. And when we look at our carbon, it's now going to be called carbon 14. And notice that after this it says radioactive. And that's because now this carbon is going to be spinning out of balance. And because it's spinning out of balance, it's going to leak energy. And that energy that it's going to leak is radioactive. And we can harness that energy and we can use it in X-rays and nuclear power plants. We can use it for chemotherapy. There's so many different uses that we can have carbon dating. And that's not taking out a fossil or an old person. Carbon dating, ha ha ha, Carbon dating is telling how old an artifact would be. If you were to go on some sort of archaeological dig and find something, you could carbon date it to tell how old it actually was. So that's carbon-14. Carbon-13 and carbon-14 are what we call isotopes because they have a different atomic mass than carbon-12 would have, which is a regular atom. So the total number of protons and neutrons in the nucleus of an atom is called the mass number, or the atomic mass, and isotopes are identified by their mass numbers, as we've seen exampled with carbon-12, carbon-13, and carbon-14. So carbon-13 and carbon-14 are going to be our isotopes. Because they have the same number of electrons, all isotopes of an element have the same chemical properties. So we're not going to see any changes. Now, we haven't talked about chemical properties yet, have we? We haven't mentioned that. There's a difference between chemical properties and physical properties. Let's just put this up here. Physical properties are going to describe, is it a metal, is it a non-metal, is it silvery, is it shiny? Those are going to be the physical properties. Is it a solid, is it a gas, is it a liquid? A chemical property is going to be how it reacts. Okay, does it fizz, does it explode, does it give off light? Those are reactions that it would have. So when we look at these, all of these have the same chemical properties. They do the same thing, they just have a different atomic mass to it. So when we take a look at the picture, here's that carbon-12 that we've been looking at before, that we've seen. We've got 6 protons, we've got 6 neutrons, and we have 6 electrons. Here's that carbon-13. We're going to have 6 protons. We're going to have 6 electrons. But let's count those neutrons. 1, 2, 3, 4, 5, 6, 7. We're going to have 7 neutrons. So when we take these two numbers and add them together, we're going to get 13. In carbon-14, we're going to have 6 protons. We're going to have 6 electrons. But when we count our protons, we're going to have 1, 2, 3, 4, 5, 6, 7, 8. We're going to have 8 protons? Neutrons, excuse me. And when we add these two together, it's going to be 14 for its atomic number. Now, this is radioactive. And it's radioactive because since there's an uneven number in here of protons and neutrons, then the spin is going to be unbalanced and it's going to leak energy. And the energy that it's going to leak is in the form of radiation. And as I said, we can use that radiation for a lot of different things. So radioactive isotopes just tells us that their nuclei is unstable. And what we know is that when being unstable, they're going to break down at a constant rate over time. We know that radiation can be dangerous. It can cause cancer and birth defects. But it also has practical uses that we can do. As I said, carbon dating, we can date the age of rocks and fossils by analyzing the isotopes that are found in them and seeing the rate of breakdown because it's constant. The radiation from isotopes can be used to not only cause cancer but treat cancer, kill bacteria that could spoil food. And we can also use radioactive isotopes as labels or tracers. We do this with viruses. We radioactivate different parts of viruses and then we see what parts of those viruses enter cells. And we found out that it's the nucleic acid that enters the cell and not the protein coat that the viruses are made up of. Or we can put, if you've ever had a CAT scan and they injected radioactive material in you, and they can follow to see if your blood vessels are open, because they can see that radiation that they put in, that radioactive isotope that they put in, and they can follow that through the CAT scan to see if your vessels are open. So these are some of the things that radioactive isotopes can be used for. Okay, looking at our time, we're 10 minutes in. The next section of 2.1 talks about chemical compounds. So our key concept here is going to be what's the difference between compounds versus elements, and in what ways do compounds differ from their component elements. So we'll take a look at that. We'll look at what makes up a compound, and we'll look at how individual elements differ from the compounds that they make. Okay, so here's our two key concepts. In what ways do compounds differ from the component elements? And the physical and chemical properties of a compound are usually very different from those of the elements from which they are formed. Alright, so chemical compounds. Let's look at the definition of a chemical compound. A compound is a substance formed by the chemical combination of two or more elements in definite proportions. You know what that sounds like to me? That sounds like a recipe. Do you cook? Okay, if you've ever cooked anything, even if it was a box cake, it tells you that you need 2 eggs and 1/4 cup of oil and 1/2 cup of milk, and it gives you how much you need. And that's exactly what a compound is. It's a recipe in chemistry. It tells you the chemical combination of 2 or more elements in definite proportions. So we can take a look at what the ingredients of a compound are, and we can put them together. For example, as I'm trying to blunder this up a little bit, water. We know that water is made up of 2 hydrogen atoms and 1 oxygen atom. And that's going to equal water. And you're all familiar with what water is. Well, what chemists do and scientists do is they kind of use a chemical shorthand. Just like when we're doing recipes, a capital C stands for cup, and TSP stands for teaspoon, and TBL stands for tablespoon. Well, we're going to do the same thing with the atoms, and we're going to use their symbols. So 2 hydrogens would be represented by 2H, and 1 oxygen, we're just going to write an O for oxygen. So when we see what water is made up of, we write that as H2O. Now notice I put this 2 in the subscript position, and that tells me how many hydrogens I have to make up water. So sugar is called glucose. And glucose, let me watch my time here, is C6H12O6. So that tells me that I need 6 carbons, 12 hydrogens, and 6 oxygens together to make up a glucose molecule. Okay, let's end this here, and then we'll continue in the next screencast.